Okay, thank you for inviting me and introducing me. I think before the break, Patrick was mentioning like he was hoping that I can introduce something that's fashion related. Here it is. It's my favorite bag. It's called, oops. Yeah, it's one of the things that we'll be talking about today. So yeah, in particular, I'm gonna talk about polytopes. And let me get into full screen. So I'm going to talk about a lower bound conjecture on general polytopes made by Grünbaum and the proof of that. And we're going to generalize it to something called strongly regular CW spheres. Okay, I'm not going to assume any background on polytopes, and it's the last talk of the day, so hopefully I don't put you to sleep. So I'm going to start from the very beginning. What is a polytope? If you take a finite set of points in RD, then the convex hull they form will be a polytope. And if you further ask that set to be affinely independent, then you get a simplex. Here are just two naive examples. And in this talk, I'll be giving you only this kind of naive examples just because I couldn't draw higher dimension. And we'll be studying faces of polytopes. And to define a face, you start with a supporting hyperplane. That is a hyperplane that barely touches your polytope. In particular, it intersects with the polytope, but only on the boundary. And then you look at the intersection. So here is a face. And you can do a different example on the right-hand side. You have another hyperplane that touches the blue one. That will make that point another face, which is a lower dimensional face. So if your face is k-dimensional, here the point is 0 dimension, then you call it a k-face, just in short. And depending on the dimension, you can give them different names. So 0 dimensional faces are vertices, and then 1 dimensional ones are edges. And for d-dimensional face, the d-1 dimensional faces are sort of the maximal proper faces, and we call them facets. And then there's the polytope itself, which is the unique D face. And we don't really care about that. And therefore we can find a vector, so-called F vector or face vector, that can help us keep record of the number of faces of each dimension. Here's the polytope that we've seen. And then because it has 10 vertices, 15 edges, and 7 two-dimensional faces, here is its face vector. Okay. I want to introduce one more definition, which is called vertex figure. So given a polytope and one of its vertices called V, a vertex figure at V is what you get by slide in a hyperplane that kind of separate that chosen vertex from the rest. And then you just simply look at the intersection. This is denoted by P mod V, and for any d-dimensional d-dimensional polytope P, a vertex figure at one of its vertex, it's always d-1 dimension. Okay, here I have the face lattices of the two polytopes on the board. So a face lattice is just, so the elements of face lattice would just be the faces, and you just order by inclusion. On the left-hand side, you have the face lattice of P. On the right-hand side, you have it for P mod V. And if you denote the leftmost rank 1 element, you just assuming that's V, then you can see that the face lattice of the vertex figure is nothing but the upper interval from V up in the original face lattice. And in other words, there's a bijection between all k faces of P that contains the chosen vertex V and the set of all k-1 dimensional faces in the vertex figure. And the bijection is quite straightforward. Say you start with a k-dimensional face in P. So for example, one dimensional face, an edge that contains V on the left-hand side, say, for example, this one, which zero-dimensional face is corresponding to in the vertex figure. Well, you can just use the same hyperplane you used to find the vertex figure and just look at the intersection there. So hopefully it's that one. Okay, so this is a very natural bijection, but it turns out to be very useful in our proof. Okay, so we're ready to state our main question. And it's quite natural again. So we fix two things. We fix the dimension of a polytope and the number of vertices. We can ask, what is the minimal possible number of I-dimensional face for such a polytope? And moreover, we can ask that, is there just one polytope whose face vector satisfy that minimal condition in every entry? In other words, is there a polytope that has component-wise minimal F vector? And we can detour a little bit. Instead of polytopes in general, we can just look at a particularly nice family of polytopes called simplicial ones. Simplicial polytopes are those whose all proper faces are simplices. Yeah, so we zoom in to that nice family, and the answer to those questions will be yes and yes. And that's called the lower bound theorem, proven by Barnett and Kalai. And they showed that stacked polytopes, which I'm not going to define here, have the component-wise minimal F vectors. So that problem is completely solved for simplicial polytopes. And we actually know the other side of the story too. So we also have the upper bound theorem, proven by McMullen, which says cyclic polytopes, also not going to define here, have the component-wise maximal F vectors among all simplicial polytopes. And there's even G theorem, proven by Bilera and Lee and Stanley, which gives a full characterization of F vectors. So it gives you all possible F vectors for simplicial polytopes. I want to emphasize here that the upper bound theorem actually works for all general polytopes, but not the lower bound theorem. So we can go back to our question and still focus on the general polytopes. So for general polytopes, we actually know very little in this problem. In fact, if n, the number of vertices, is greater than 2 times the dimension, we didn't even have a conjecture. We only had a conjecture made by Grünbaum in 1967 for relatively small number of vertices. So that's when n is up to 2D. And here's his conjecture. So here, number of vertices up to 2D. So we say it's D plus S when S is at most D. And Grünbaum conjectured that the number of K faces for such a polytope will be at least this alternative sum of binomial coefficients using K, D, and S. And since we'll be working on this formula through our talk, we'll give it a name. This is also Grünbaum's notation. So in the parentheses, the first entry is the number of vertices. The second one is the dimension. Here's a picture of Grünbaum. He actually worked in Seattle most of the time. Okay, so previous results. Grünbaum himself proved the first several cases when S equals 2, 3, and 4. That's when the polytope has D plus 2, D plus 3, and D plus 4 vertices. When S equals 1, well, there's a unique D-dimensional polytope with D plus 1 vertices, which is a simplex, and it will trivially satisfy this formula. And the next result that we know was from a paper in 2019 by the following 3 authors. sorry, I'm pretty sure I would mispronounce the name, but they are Pineda, Villa, Vincencio, Yugon, and Yost. And they prove for the case when k equals 1. Well, k is the dimension of the faces in this formula, so that's the case for number of edges. And then in 2020, what I was able to show is that the conjecture is true, and it's true for all dimension d, all possible s's up to d, and for all k. Okay. And I probably should pause here. Is there any questions so far?
So maybe you mentioned it, but I missed it. But is the conjecture also that there is a polytope which minimizes it for each k simultaneously?
Yes. So yeah, that's actually the second part of the.
Oh, okay. Top. Sorry, then I'll.
So this is the inequality case, and we will be treating the equality cases later.
Wonderful. Great. I look forward to that.
Mm-hmm. Okay, so we're moving to the proof of this theorem. And there's a very important proposition that I use in the proof, and I call it key proposition. Now, let P be just a deep dimensional polytope, and we don't care about that restriction on vertex number. We just pick a random set of vertices in that polytope. We pick n vertices, m up to d. They don't have to be related to each other in any sense, but we just count the number of k faces of P that contain at least one vertex from the set. And then this number is bounded by the summation of binomial coefficients on the right. And here's my hand wavy sketch of the proof. So the proof uses vertex figure. So let me just remind you what it is. And in particular, I had the two face lattice on the board again. Okay, so we want to use vertex figures, and in particular that nice bijection. We start from, so first of all, we order the n vertices in a random order, doesn't matter. And we can count the number, the k faces of P that contains V1 by just looking at that upper interval there from V1 to top. And then we kind of want to do it for the rest of the vertices, but now as we move on, we need to consider our choice so we're not overcounting. So when we move to V2, we want the k faces of P that contains V2, but we want to avoid V1. So instead of the vertex figure at V2, we look at still the vertex figure, but inside a facet of P. So it's sort of like to me, it feels like we're sacrificing a dimension, but now to avoid overcounting. And we can keep doing that. At each stage, we're looking at some vertex figure of one of the vertices, but inside a lower dimensional face. And eventually, and you bound the size of, you bound the number of k minus 1 faces in those upper intervals in order to get the summation of binomial coefficients on the right. Okay. And then we can jump directly into the proof of the main theorem. And it will be an induction on S. And recall that S, D plus S is the number of vertices. The base case or the several first cases are done by Grünbaum. And this is all we need to show. So assume that it holds for some smaller s, and then d, at least that s, you want to show it for d and s. Okay, we start by picking a facet f, and all we need for f is that it has at least 2 vertices outside of it. So we can do the induction. And we label so in this naive picture, the green part is F, and we label the outside vertices, V1 through Vm. And we can start counting immediately. So we want to count this. K faces of P, and they will fall naturally into two categories. Either it's a K face of F, or it should contain some of the outside vertices. If it's the first case, we use the inductive hypothesis. If it's the second case, we use the key proposition. And therefore, you can bound Fk of P by the summation of the red part and the blue part coming from the key proposition. Well, these are all binomial coefficients, so we arrange them a little bit using either just Pascal's identity or some other binomial coefficient identities. Really, I'm not hiding anything mysterious from you. But at the end, you will get what we want, which is phi k d plus s d plus something which hopefully is non-negative. And it is because in each segment, notice that here, M is the number of vertices outside of facet, and the facet has at least D vertices. So M is at most S. And that's basically the proof. The only case that we're missing here is that what if we cannot pick such a facet F in the first place? But that's exactly when for each facet of P, there's only a unique vertex outside of it. So in particular, P will be a cone over a facet, which is also a cone. It's a cone over a cone over a cone. It has to be a simplex. Yeah, so we're done with the proof. Is there any question about the proof? Okay, great. So now we move to the treatment of equality, the question that Patrick just asked. So here's the question. Which polytope satisfies this equation? Actually for all case. And we can also ask, like, are there other polytopes that satisfy this just for some of the case? And so for the first question, like for all case, we're asking like which polytope has the component-wise minimal F vector. This is sort of done by Grünbaum because Grünbaum made that conjecture, like that mysterious formula, because he had some family of candidate polytopes in mind. So once we show the inequality, we actually have a minimizer. And to repeat his conjecture, his construction of those polytopes, I need to define a few more things. So first of all, I want to define what it means to say that a point in RD is beyond a facet of a polytope. Well, from the picture, it looks very intuitive. It is, but rigorously, you use the supporting hyperplane of the facet again. And the point is beyond that facet if that hyperplane has that point on one side and the entire polytope on the other side. And once we define that, well, given a point and a polytope, you can count how many facets that point is beyond. So this yellow vertex is beyond one facet. It's beyond this, the most, like the top one, because of this hyperplane that separate the two parts. But if I move it here, then it's actually beyond two facets. This one, yeah, the following one on the board. Another way to understand this is to imagine that you're standing at that point X and you are counting how many facets you can see from that point. Okay. And the construction also uses dual polytope. So let me quickly define that. If you're given a polytope P, the dual P star is a polytope of the same dimension. So it's also a d-dimensional polytope, but it's just its face lattice, it's the flip over of the original face lattice. In particular, here in this example, if I look at this face, this facet of the green polytope is corresponding to a vertex. Somehow you're not seeing my marks. Hopefully it will show up in a few seconds. Oops, that's because I'm not connecting. Okay, I think I'm back. And I was writing, can you see this?
Yes, we can.
Okay, so we look at this facet of the green, this one, polytope, and it's corresponding to this vertex of the purple one. In particular, you can see that the facet in the green polytope has contains 4 edges, and the vertex in the purple one is contained in 4 edges. Okay. And now we can use Grünbaum's notation to define Grünbaum's polytopes. It's not complicated. So we start from a simplex, and we put a new vertex beyond exactly m facets. And there's only like up to equivalence, only one way of doing that. And you can probably tell that putting a new vertex beyond the facet doesn't really change the dimension of the polytope. So you still end up with an 8-dimensional polytope, and it's still simplicial. And then you just do the pyramid operation d minus 8 number of times. So, or in other words, you're coning over it d minus 8 number of times. That will increase the dimension by d minus 8. So you will end up with a d-dimensional polytope, and after coning that many times, you're probably not gonna get a simplicial or simple one. So here, yeah, there are many notations. There are many parts in this notation. So in the superscription, d means the dimension, and then d minus 8 denotes the number of pyramid operations that you take, and m denotes how many facets of the simplex is your new vertex beyond in the first step. Okay, naive example again. Here's a 2 simplex. In order to get T2 sub 1, we want to add a new vertex beyond exactly 1 facet. So how about this? Right, this orange point can only see 1 facet, couldn't see the other 2. And you add it, so it's now a new convexo. And then because I can only draw up to 3D, so I can only take 1-fold pyramid, and that will give us T3, 1 sub 1. It might take 5-10 minutes to play with it to get used to all those indices, but really, just by observing this construction, hopefully you will agree that it should be very easy to keep track of the F vectors through these operations. And if you are familiar with polytopes, you'll be wondering, isn't the first operation just the direct sum between 2 simplices, and the second operation just joining another simplex? You're right. I chose Grünbaum's construction just because it's more intuitive and easier to define. Okay. Yeah, so there's several lemmas about these nice family of polytopes. First of all, Td sub m is actually equivalent combinatorially to Td d minus m. That means if you add a new vertex above m facets of a simplex, it's the same as adding a different vertex, like beyond exactly d minus m of them. So if you want, you start from T3, the 3 simplex, and to get T3 sub 1, you add this orange point, which is exactly above this facet. Okay, that'll give you this. And then to get T3-2, you add this brown one, which can see two facets. Doesn't make sense. This brown one can see this one and this one. And now you can rotate your head to see that they're actually the same. Right. Okay. Lemma 2 says that, well, in fact, every simplicial d-polytope with exactly d plus 2 vertices is one of these. So this construction will give you all possible simplicial ones with d plus 2 vertices. And finally, here's a relatively nice formula for the F factor. Yeah, for certain K, A, and M. And this is nice because in particular, if you let M equals 1, A equals S, and you dualize the polytope, that's where Grünbaum's magic number comes from. And if you're following very closely, what we just did is to say that this polytope is the winner. It has the component-wise minimal vector. Okay, but is it the unique winner? Like, is there any other minimizer or just partial minimizers? With that equality hold for some case, not necessarily for all case? Well, to show that, we need to go all the way back to the proof, and even further back to the proof of the key proposition, and really examine all the inequalities, and to see when they are equalities. Like, all of them should be equalities. And yeah, and then you will get a couple of corollaries, which would be very important. Will make the proof for the equality case quite easy. So the first corollary says that for each facet of such a minimizer, you don't have that many choices for number of vertices. Okay, you only have 3 choices. And secondly, every non-apex vertex has to be simple. And by that, so simple means that that vertex is connected to exactly D other vertices by an edge. And the third one is the most powerful one. It says that such polytope must have exactly D plus 2 facets. And that's the most useful one because now I can flip it then and look at a polytope with exactly D plus 2 vertices, and we know that family quite well in the past 5 minutes, right? So what we do is that we use the second corollary to sort of get rid of all the apex vertices. So we decone whenever we see a cone and end up with a simple polytope, right? With, and then we flip it. So we actually end up with a simplicial polytope with exactly D plus 2 vertices. And that will help us prove that the minimizer we just found is actually the unique minimizer. So if you have this equation Fk equals Vk for some k, when k is between 1 and D minus 2, then P has to be that polytope we just found. And you may notice that here k only goes up to D minus 2, and that's because when we know only know the equation holds for k equals D minus 1, D minus 1, well, that's the case when you fix the facet number. And the minimal facet number, we know it's D plus 2. So we're fixing the number of vertices and the number of facets. And in general, any member of the family that we just saw can be a candidate, can satisfy those conditions, as long as you can find A, M, and then S satisfying these inequalities and equalities. So in very special case, for example, if we focus on this equation, when S is some prime plus 1, for example, then the minimizer is still unique, but it's not true in general. Okay. And so we're done with the equality cases. And one natural, so we try to generalize the result now that Grünbaum's conjecture is proved. One direction is to prove it for a more general setting, and it's natural because of the fact that the proof and the key proposition are quite are relatively short, and it doesn't seem that use anything particular about polytopes. So maybe it still holds for larger sets. And the larger set we found is a set of all diamond lattices. A diamond lattice is a finite lattice where every interval of rank 2, it has exactly 4 elements. So it's of a diamond shape. And this is particularly nice because in the proof of Grünbaum's conjecture on polytopes, one fact that's simple, but it's quite important, we use it over and over, is that facets of polytopes can distinguish vertices. In other words, if I have 2 vertices, there's always a facet that contains one, but not the other. And diamond lattices satisfy the same condition, just in lattice language, in poset language. So co-atoms or higher ranked elements will be able to distinguish atoms. So you can always find a co-atom that contains, that covers one atom, but not the other. And because of that, you can basically take diamond lattices and use this co-atom distinguishability proposition and push it into the proof of the key proposition and the proof of the main theorem. It will pass the machine just fine. So we're able to actually generalize it, this theorem, to diamond lattices, basically by prove the basic necessary properties, and then just rewrite the details of the proofs in poset language. And then for the equality cases, in particular, the uniqueness of the equality case. Well, you can probably imagine it cannot be generalized to all diamond lattices, but we generalize it to the following family in between, which is called strongly regular CW spheres. We actually prove it. I think the strongest result we got, actually, we prove it for some of those strongly regular CW pseudomanifolds, but to keep it simple in this talk, we'll just be focusing on CW spheres. So CW spheres are just CW complexes homeomorphic to spheres, and they're regular if the attaching maps are actually homeomorphisms. And we call them strongly regular if, in addition, you have the following intersection property, which says the intersection of any 2 closed cells or disks is also a cell. It can be empty, it just cannot be more than 1 cell. And here's to show you that this is indeed a much bigger set than the set of polytopes. There's some spheres coming from oriented matroids in this family, and also regular PL spheres. Okay, so one simple fact about these strongly regular CW spheres is proven by Kleinschmidt. So basically, any strongly regular CW spheres with exactly d+2 vertices are boundaries of polytopes. And this will help us prove the generalization of our uniqueness equality case, uniqueness of the equality case theorem. Okay, so these are the generalizations in this direction. Another direction that one can think of is to push the limit of the number of vertices. Recall that I mentioned there wasn't a conjecture for n greater than 2d, and it seems there's a reason, but one can think if we just add 1 more vertex. So we stop at 2d, what if we just look at the 2d plus 1 case? It falls immediately after that bound. So I'm going to show that when f0, the number of vertices, equals 2d plus 1, then at least for half of the case, or almost never, almost always, that the component-wise minimum F vector does not exist. In particular, I'll give you two polytopes, P1 and P2, and together they'll give you a contradiction, like neither of them will give you the component-wise minimizer. So P1, as you can see on this, on the board, they're all sort of, they're both sort of adjusted version of, or you do little changes on Grünbaum's polytopes. For P1, you start with this d minus 2 sub 1 polytope. You first stack over a facet of it, which is a simplex. So you stack over a simplex facet and then dualize. This is called a pentasome. Here's a 3-dimensional pentasome, which explains the name. And P2 is another polytope in Grünbaum's family. And in particular, P2 is only defined when D is even. So they both have exactly 2D plus 1 vertices. And in the same paper from 2019, Pineda, Villa, Vincencio, Hugo, and Yost, well, that was the paper on edge numbers. So they actually showed that when D is at least 5, P1, the pentasome, is the unique minimizer on edge numbers. Okay, but because you stack before taking the dual, it has strictly more number of facets. So these in front of you is straightforwardly showing you that it's impossible in this case to have component-wise minimal F vector when n equals 2d plus 1. Okay. Well, but all is not lost. So we just showed that there are two polytopes. One is the minimizer on one end, sort of, on edge number, and one is the minimizer for facet numbers. The next best thing you can have, if you're optimistic, is that can they combine and give you a lower bound? And it turns out that they can, and it's very surprising. So what we're able to show is that, while we're also able to show it for spheres, not just polytopes, is that if your vertex number is at least 2d plus 1, then if your facet number is exactly d plus 2, then P2 will give you the bound. If your facet number is greater or equal to d plus 3, then P1 will give you the bound. And in particular, if you compare the F vectors of P1 and P2, basically P1 is dominant, is lower in the first half, and P2 lower in the second half. And I just also want to mention that this was like a similar result for polytopes was also proven by the same group of authors in their recent paper. In particular, they showed that if you have a polytope with exactly 2d plus 1 vertices, then Fk is bounded either by P1 or P2. And somehow it's a little bit shorter than I expected, but that's the end of the talk. And I Googled this too.
All right, thank you very much. Are there any questions? That doesn't seem to be the case. I guess after 3 hours of talks.
So, I mean, one question I want to ask, I mean, there's this question of Barani or Gill, that somehow if you have a polytope, okay, let me say it in this way. So if you have a polytope, and in the first half, the face vector is minimized by the vertices, and then in the second half, the face vector is minimized by the facets. Have you ever thought about that?
Sorry, are you saying there's a known result?
No, it's a conjecture.
Oh, no, I've never heard of it. I would believe it after after this result for n equals 2d plus 1 case. So like it. Can you say that again? What's this conjecture? And do you know who made the conjecture? I think you're muted again.
It's by Barani and by Gil.
I see.
So Karai. Okay.
Yeah, that
it might be interesting for you.
Yeah, that's a good. I've never heard of it. I'm gonna research that.
All right. Thank you for your talk.
Okay. Are there any other questions? Doesn't seem to be the case, so I'll